everyone, this is Brenna, your friendly 121 LA, with a problem on spring constants and simple harmonic motion. This problem says the Achilles tendon will stretch and then rebound, storing and returning energy during a step. We can model this motion as that of a mass on a spring. It's far from a perfect model, but it does give some insight. If a 60-kilogram person stands on a low wall with his full weight on the ball of one foot and the heel free to move, the stretch of the Achilles tendon will cause the center of mass to lower by about 2.5 millimeters. Alright, so let's start with the first one, which is what is the value of K for this system? But I think to start, we're going to have to draw a picture. So I'm going to draw a picture. Here's the wall. And then we have this person who is standing on the balls of their feet, with their heel free. So kind of like that. We know that the person's mass is 60 kilograms. We know that the compression of the tendon here, right? Let's say the tendon is here. The compression of that tendon, so we'll just call that delta Y, is 2.5 millimeters. Right? We know that because if all the weight is on this 1 foot, then we get shorter by 2.5 millimeters. We also know that all of the weight is on 1 foot in this case. And first we are asked to find K. Well, K is the spring constant. And I first just want to look at the units of the spring constant. The K has units of Newton meters. So the force applied to the system, to the spring, over the distance compressed. And we have both of those things, we can find both of those things, because in this case, K is just going to be equal to the weight force, which is what compresses the spring in this case, and the distance is just going to be 2.5 millimeters. So if I go ahead and do that calculation, I have mass times gravity over 2.5 millimeters to meters divided by 1,000 is 0.0025 meters. And if I go ahead and do that calculation, 0.0025, I get a spring constant of 2.4 times 10 to the 4th Newton meters. Alright, so that's our K. We're asked next to, given the mass and the spring constant, what would you expect for the period of this system were it to undergo an oscillation? So for B, we're looking for the period. Well, we know how to find the period for a mass on a spring. It is just equal to 2 pi times the square root of the mass over K. And we can go ahead and do that calculation. So it's 2 pi over times 60 kilograms over the spring constant, which is 2.4, times 10 to the 4th Newton meters. And if we go ahead and do that calculation, I'm going to do it. I haven't done it before right now, so we'll do it together. Actually, let me figure. So 60 divided by 2.4 times 10 to the 4th. And we're going to take the square root of that. And then we're going to multiply that by 2 times pi. Okay, so I get a period of 0.314 seconds. Okay, well, if we think about the rest of the problem, we'll really be able to assess this later, but it says when you're running, you keep each foot in contact with the ground for about 0.1 seconds, some of which corresponds to the heel strike and subsequent rolling forward of the foot. So I'm going to say, okay, if our total period is 0.3 seconds, then that means that the time that we hit the ground is a third of that. And that seems pretty reasonable to me so far. So let's go ahead and think about the next question. It says, when the ball of the feet take the weight of the stride, the tendon spring begins to stretch as the body moves down. So this is that compression piece we were talking about. Kinetic energy is being converted into elastic potential energy. Ideally, when the foot is leaving the ground, the cycle of the motion will have advanced so that potential energy is being converted to kinetic energy. What fraction of an oscillation period should the time between landing and liftoff correspond to? Okay, so let's think about it. So at this point, I know that we are, well, let's just draw a picture. I think that's the easiest way to do it. So here's the ground. We are coming into contact with the ground, and pardon my feet, they kind of look really bad. We're coming into contact with the ground when we land. We then end up with this phase where we're not doing anything and our speed equals 0, right? This is where we're at rest. And then we are moving up again. Okay, so now I'll just label it like this. I think we should draw a graph, a position versus time graph. So if I draw a position versus time graph, I start at a positive position, right? And then I am going down to 0, right? And then I'm moving back up again. And we have this sort of repeating motion here. This is our oscillation, okay? At this point is when we are landing. And at this point is where we are taking off again. If we think about this graph here, one wavelength is from trough to trough or peak to peak. So we'll just do trough to trough because I think that's easier to think about. So this distance here is one wavelength. That's one cycle, right? So ultimately we're looking at the period for this process here. From the time you land to the time you land and transition to taking off again. So we're asked to find what fraction of an oscillation period should the time between landing and liftoff correspond to. Well, that's this point right here, right? If we look at our wavelength in terms of peak to peak, well, shoot, that's half a wavelength, right? If it's half a wavelength, it's half of a cycle. So our time between that, for that transition period, so time is going to be equal to half of the period. Okay, well, I know that the time is half of the period, so let's just go ahead and calculate that. And if I do that, I get 1/2 times 0.314 seconds. I get a time of about, oh, let's see, 0.314 times 0.5. We get a time of about 0.157 seconds, which is what it asks us in D. We found the time. Now it says sprinters running a short race keep each foot in contact with the ground for about 0.1 seconds, some of which corresponds to the heel strike and subsequent rolling forward of the foot. Given this, does the final number you have calculated above make sense? Well, 0.1 seconds is not a long time for a foot to be in contact with the ground, but that's basically what we figured out here, right? Because 0.157 seconds represents this time right here. The time in between coming down, and landing. Or landing and going up. So I would say yes, this makes sense because ultimately our foot is only going to be in contact with the ground for a very short period of time. Once we start moving up again, our foot is leaving. And we no longer really become in contact with the ground. So I would say yes, this makes sense given the data above and real life experience. And I think that is all. I'll see you in the next one.